We are in the middle of a massive transportation shift. With prices at the pump climbing steadily, the push to transition away from combustion engines has never been stronger. And there is a serious secondary benefit to this transition. The endless rumble and mechanical noise of gridlocked city streets is steadily being replaced by the quiet hum of electric alternatives. But beneath the promise of a silent, emission-free commute, there is one specific piece of hardware that dictates whether an electric vehicle actually makes sense to own. It all comes down to the motor. Automotive engineers have wrestled with electric propulsion for over 100 years, trying to figure out the most effective way to turn battery power into forward momentum. The math is unforgiving. If a motor is inefficient, it bleeds battery power prematurely, drastically cuts your driving range, and destroys the vehicle's total cost of ownership. Today, the industry is split between two distinct choices: the traditional brushed DC motor and the modern brushless BLDC motor. If you are shopping for an EV, you will immediately notice a steep price divide. Buyers face a heavy premium for vehicles equipped with BLDC technology, while traditional DC models sit at the bottom of the budget tier. This blank chart illustrates the core tension of the electric vehicle market. Getting the range you need for a modern commute means navigating this exact trade-off, balancing your upfront cost against long-term energy efficiency. We are going to strip away the marketing buzzwords and look closely at the raw mechanical realities of how both of these systems generate spin. Understanding the literal nuts and bolts of these engines is the only way to know exactly what you are paying for and what you are sacrificing. Let's start with the traditional DC motor. It is one of the oldest, most foundational types of electric propulsion available. To operate, it relies on physical carbon blocks called brushes, paired with a rotating cylinder known as a commutator to continuously flip the direction of the electrical current. As the current flows, the motor spins. But to keep that current switching, those carbon brushes must maintain constant physical contact with the copper commutator while it spins at thousands of RPM. This setup is incredibly simple. It makes the motor exceptionally easy to wire up and highly effective at generating mechanical rotation. That simplicity keeps manufacturing costs extremely low. However, forcing two physical parts to rub against each other during operation introduces an inescapable mechanical flaw. The immediate consequence of utilizing internal brushes is severe, relentless physical friction. Friction creates heavy heat. In an electric vehicle, any heat radiating off your motor is literally valuable battery energy being wasted, rather than pushing your tires forward. Because the carbon brushes physically wear down as they scrape against the cylinder, they inevitably require replacement. This guarantees future maintenance and downtime for the vehicle. You tolerate these drawbacks for one specific reason. These units are incredibly cheap to manufacture and inexpensive to replace. A traditional DC motor provides absolute, unmatched upfront affordability, but it demands steep sacrifices in long-term durability and efficiency. That mechanical flaw pushes the industry toward the modern alternative, the brushless direct current, or BLDC motor. This is the hardware dominating modern electric vehicles. The core design leap is in the name. Engineers took the traditional architecture and completely stripped the physical carbon brushes out of the motor entirely. Without brushes to flip the current, the system relies on an advanced electronic speed controller. It acts as the system's brain, rhythmically firing precise pulses of electricity directly into the motor's stationary coils. Removing those physical contact points eliminates the internal friction. The immediate result is a drastic reduction in heat generation. The BLDC motor takes the heavy burden of mechanical wear and tear and transfers it over to silent, highly precise electronic processing. Now, let's weigh the cost and complexity of these two motors directly against their performance outputs. Looking at this matrix, traditional DC relies on physical brushes, while modern BLDC utilizes a complex electronic controller. DC scores high for friction and energy loss. BLDC registers zero physical friction. However, DC offers a cheap setup, whereas BLDC requires a high upfront premium. You cannot buy low upfront cost and high long-term efficiency at the same time. You have to pick which side of this matrix aligns with your specific goals. Let's map this data onto a flowchart based on a single question. What is your primary priority? If you're a DIY hobbyist building a weekend toy or shopping for a budget e-bike, your path flows left. The DC motor is the correct choice here. Securing cost savings and simple wiring is vastly more important than squeezing every mile out of the battery. However, if you commute daily or drive a premium EV, your path moves right. Mapping the motor to the exact use case guarantees you won't waste money over-engineering a weekend project and ensures you won't strand yourself by under-equipping your daily transport. Zooming out to the broader automotive market, the verdict is already in. Nearly all major modern electric vehicle manufacturers have universally adopted BLDC systems. In high-stakes EV engineering, every ounce of heat generated by motor friction is a mile of driving range erased from the dashboard. Ultimately, long-term efficiency simply outranks upfront cost. Traditional DC motors built the mechanical foundation that proved electric power was viable. But as electric vehicles continue to grow, the silent momentum on our roads is driven by the cleaner efficiency of brushless technology.